right, let's get started on this. Is there any questions about previous material for upcoming exam? I know on my announcement I indicated from chapter 1, but I meant lecture 1, okay? And your exam will stop wherever we stop today, okay? No questions? Everything clear? All right. Karen?
Are your exams based on your lectures or like everything's textbook?
Based on my lectures.
Okay.
Okay. That's a very good question. Whatever we have talked about, even though it might not be your textbook, can be on your exam. It's about our lectures, okay? I'm not testing your ability to read the textbook. I'm testing your ability to comprehend the material.
Okay.
Other questions? Sana?
Anything from the lab?
Well, this is other students have asked that question. You got to realize that lab material and lecture material, they're not separate entities. Okay? You're going to get one final grade at the end of the class. However, the focus will be on what we cover in the lecture. Now, if I have told you something, for example, about MCV in the laboratory, that you have to use it in order to be able to answer the questions in the lecture, that's quite fair game. You cannot come and say, oh, you told us in the laboratory that doesn't work, okay? So it's comprehensive, but the topic is going to be on the material that we have covered in the lecture. But that does not mean you're not going to need information that you have acquired in the laboratory. But the focus will be on the lecture material. And the same thing goes for the laboratory. The focus will be on the laboratory material when you have the exam for the lab.
Is there a quiz
Karen?
on the exam day?
I'm sorry?
Is there a quiz on the exam day?
No.
Okay.
There will not be any quiz on the day that you will have exams. Other questions?
You use a lot of diseases to explain some of the mutations or chromosomal diseases.
Sure.
Do we have to know those exact chromosomes
I do not place too much emphasis on the memorization. I've said that many times in class. So I am not trying to see how well you're going to be able to memorize things. But again, I don't want you to think that, okay, let's just go off that. There is going to be time that you will come across chromosomal diseases that I specifically emphasize. This is the chromosome that you have a problem with. The example would be when we are talking about the hemoglobin. There are specific genes that are going to have these genes on these specific chromosomes. I will mention that, then I will expect you to know those. But all those different diseases that we have spoken about so far, I want you to understand the disease. I want you to understand how that disease is formed, is created, is developed. But asking, for example, is it on chromosome 12 versus chromosome 6, I don't find anything interesting about that. Other questions? All right, let's get started then. We're going to start on chapter 9. This is going to be lecture 6. And we're going to talk about red blood cell metabolism. Folks, this is a very interesting situation in here. You've got to think about this. Just you got to sit back and you got to enjoy the unique situations that red blood cells are in. What is the primary function of the red blood cells? Transport oxygen. Okay? Now, it happens to be that there is an organelle inside every cell that uses the oxygen. What is the name of that organelle? Mitochondria. And it's interesting that when the red blood cell loses its nucleus, when it's going to come out of the bone marrow, it also loses all of its organelles. So red blood cell that is mature in the circulation is not going to have mitochondria. Isn't that amazing? Even in nature, you're not going to trust everybody. You're going to give the oxygen to be carried to a person who's not going to be able to use it. Think about that. How fascinating and effective that mechanism is going to be. Because if they have mitochondria, they use it up. So your cells at the tip of your fingers are not going to get enough oxygen because red blood cells would have mitochondria and they're going to use up the oxygen. But red blood cells do not have mitochondria, and they are going to be a safe keeper of oxygen and deliver it to the place that's supposed to be delivered to. Okay? Now that's going to create the situation, because despite the fact that red blood cell does not have any mitochondria or any nucleus, we are talking about the mature red blood cell, of course. there is still need for the production of ATP. What kind of need we are talking about? Let me give you a couple examples so things make sense to you. I have already told you about the cell membrane. You all know about the plasma membrane, very unique characteristic of this biphosphate layer. One of the things that this plasma membrane is going to be able to do is that it's going to create gradients. So you will have much more sodium outside of the red blood cell than inside of the red blood cell. You have 12 times more sodium outside than inside. Why it did not equalize? Because of the cell membrane. You have 25 times more potassium inside of the red blood cell than the outside of the red blood cell. How is that possible? Because of the plasma membrane. Does not allow the free movement of ions or anything that has polarity. You are having 1,000 times calcium in the plasma compared to the red blood cell. How is that possible? It's the plasma membrane. Now this plasma membrane, like anything else, there's going to be wear and tear of it. There's going to be damages that are going to happen because how long the red blood cell is going to survive in the circulation? 120 days. That's about 4 months. So you have to have a mechanism in order to be able to repair damages to that red blood cell. You want to repair? When you go to the mechanic, what do they ask for? They ask for your credit card.
Yeah.
Okay? And this is what it is. This is a credit card, ATP. You got to go ahead and make ATP. Now you don't have mitochondria. How are you going to be able to go ahead and make ATP? The answer would be glycolysis. Remember glycolysis when we were talking about glucose breakdown. We are talking about the glucose. You eat that cheese sandwich. That cheese sandwich goes inside your stomach, mix up with stomach acid and enzymes, goes to your small intestine. It's going to be broken down to small subunits. Your carbohydrates are going to be broken down into glucose. Your proteins are going to be broken down into amino acids. Your lipids are going to be broken down into glycerol and fatty acids. Then you would be able to absorb them. This process of turning the cheeseburger into the subunits is called digestion. And then you would be able to absorb the glucose. Otherwise, if you don't break that glucose to carbohydrate into the glucose, everything that comes in is going to go out without being absorbed. You have to break it down into subunits. Alright? The glucose in the plasma is going to supply the source of energy for red blood cells. Because the movement of the glucose into the red blood cell doesn't need ATP. It needs a transporter that is going to be able to allow glucose to move from the plasma into the cytoplasm of red blood cells. But that process does not require ATP because you have higher concentration of glucose outside, you have lower concentration of glucose inside. Diffusion allows it. But the problem is that glucose is a big molecule, so you got to have a gatekeeper. And that gatekeeper, all he's going to go ahead and do is going to maintain the integrity of the membrane. At the same time, he's going to allow the glucose to come into the cytoplasm without spending any energy, without spending any ATP. Wonderful. But that membrane, I told you, is going to be broken down. It's going to become oxidized. Now, some of you haven't had chemistry, so what I want you to understand about the words that I'm going to use today called oxidation and reduction is this. When a molecule becomes oxidized, it's not going to be able to do what it's supposed to do. Let's just put it that way. Very simple language. If you don't remember anything about chemistry, you can remember this. If you want that molecule that was oxidized and is not able to do what's supposed to do, to be able to do what's supposed to do, you got to reduce it. And molecules inside of our body continuously in the stage of reduction and oxidation. You don't want always the light to be on. You want the light sometimes to be on and sometimes to be off. If you want to go in and turn off that enzyme, oxidize it. Take a phosphate off it. If you want that enzyme to become active, reduce it. Add a phosphate to it. So this is the way you're going to go in and turn things on and off inside of cell. Your red blood cell, one of the major needs for the ATP is going to be to maintain the plasma membrane in a reduced state. We will talk about some of the things that's going to happen if that doesn't happen. That ion gradient, that 12 times higher sodium concentration outside, 25 times higher potassium concentration inside, you are going to maintain that. Yes, it is true that the plasma membrane is going to be very important, but you have these pumps that are continuous. We call them cation pumps. These pumps are continuously pumping, for example, sodium out, potassium in. Sodium out, potassium in. The key about this is like that. What did I tell you is going to be the concentration of the sodium outside of the cell in the plasma? How many times more than the inside? 12 times. So if I am going to get a sodium from inside of the cell and pump it outside, am I going to go with the gradient or am I going to go against the gradient? Am I going to get from low concentration to high or am I going to get it from the high concentration to low? Anytime you are going to get something from a low concentration and pump it to the area that's going to have higher concentration, you need ATP. Without exception. You always will need active transport, and active transport requires ATP, requires energy. In order to maintain that gradient, you need to use ATP. If you don't have enough ATP, what's going to happen? What do you think is going to happen? If you are unable to get the sodium out of the cell and put it in the plasma, what do you think is going to happen? You all have enough knowledge to be able to think about this and get me the right answer. You have the background now. I gave it to you, so I know that. What do you think is going to happen if the red blood cell is unable to supply ATP for those pumps? Let's go ahead and have the sodium as a good example. What's going to happen to the red blood cell if it cannot get the sodium out? Oh, that's what it is, people. If the sodium doesn't go out, what is going to come with the sodium inside of the cell? Water. What was the shape of the red blood cell? It's by a discoid, right? It was a discoid shape. This was the normal. If you're looking at the side of the red blood cell, it's going to be shaped like this. Now, if you are unable to supply the ATP for these pumps, sodium is going to come in. It's not going to go out. Water is going to come with it. When the water is going to come with it, it's going to become what? It's going to be spheroids. We have a name for this. Spherocytes. Now, the problem is this, that this shape is able to change its shape. This red blood cell is able to change its shape, to go through small blood vessels, to go through small network of reticular fibers in the spleen. These fibers in the spleen that I'm talking about, they are about 2 microns. What was the average diameter of a red blood cell? 6 to 8 microns. So that's going to pose a problem every time this red blood cell is going to go through the spleen. If you are like this, you can squeeze your vein. If you are like this, you cannot. And that's what's going to happen to the red blood cell that cannot supply ATP. It's going to swell up, it will get caught in the spleen, and macrophages will take care of the business. Okay? So you understand the importance of ATP in a red blood cell that doesn't have mitochondria, doesn't have nucleus, doesn't have any organelles. But it is important to produce ATP, and we are able to do that by glycolysis. Now, glycolysis is going to require a bunch of different enzymes. But these enzymes are going to be all in the cytoplasm. They're all in the cytoplasm. And they were all made when the red blood cell had this nucleus. They were made, they put inside of the red blood cell cytoplasm, and they are able to generate ATP as the red blood cell goes through its life journey. But it's true, these enzymes are not invincible. There is oxidation, there is damage to these enzymes, so gradually as time goes by, we are talking about 120 days on average, as the time goes by, these enzymes lose their ability to produce ATP. Cell of the red blood cell is gradually from the discoid is going to become spherical. This is one of the things that happens to an old red blood cell. If you're wondering, why 120 days? Why not 150 days? Why not 260 days? Because of the fact that we have measured that it takes that long for for the red blood cell to lose its ability to produce ATP. Reds are going to become spherical, and what's going to happen is that they are going to be destroyed in the spleen. Glycolysis is the primary way for the red blood cell to generate that ATP that needs for things like that. Okay? Let me do something here. I want to use the board because I want to use the entire board, so I want to go ahead and raise the screen in here, then I'll go over the lecture at the same time. Let me just remind you of glucose. That's in the plasma. It's going to be able to, without spending any energy, it's going to be able to come inside of the cell. There are enzyme, glucose phosphate, that's a kinase that's going to be able to put a phosphate on this glucose, and it's going to make this glucose 6-phosphate. And the reason is that if that was not being done, glucose can get out of the cell again. By putting the phosphate, you're going to make sure that it's going to stay inside of the cell. Then the process of glycolysis is going to take over. There are a bunch of different enzymatic reactions that ultimately is going to push this to become pyruvate. Pyruvate is going to be able to go on different journeys. Anaerobic respiration, you're going to ultimately get into lactic acid. But the net production of ATP is going to be 2 ATP. Or you can get pyruvate into the mitochondria, Krebs cycle, electron transport chain, and you would be able to make something around 36 ATP. We are talking right now, the focus is going to be from glucose down here to the pyruvate. This process, you are going to be able to generate 4 ATP, but during this process, you're going to use up 2 ATP. For the net production of ATP for glycolysis is going to be 2 ATP. Okay? But there are going to be shunts. There are going to be extra pathways. These extra pathways, they don't produce ATP. Some of them actually use up ATP. So you gotta wonder, why we are having these extra pathways? Why are we having these pathways if they are not gonna go in and do any good? Well, they're gonna do good. They just don't produce ATP. Let's look at a couple of these pathways. This glucose 6-phosphate with the enzyme, we're gonna call that enzyme G6PDH. This is D. Glucose 6-phosphate dehydrogenase. Sometimes they don't put the H. I like to put the H not to mix it up with this one. G6PD or G6PDH is glucose 6-phosphate dehydrogenase. Sometimes this glucose 6-phosphate, instead of going toward the pyruvate, what it's going to go ahead and do is going to be converted into another molecule. We call that molecule a pentose sugar, or pentose sugar is fine. Really, the name of the molecule is not important in this case. And that pentose sugar is going to come later on, is going to join and continue going that same direction as the glycolysis. I just don't understand what is the purpose of this extra step. In nature, if something is not necessary, it's going to disappear. Things that are necessary will stay around. There's a very good reason for that pathway. Okay, this is called hexose monophosphate shunt. Hexose monophosphate shunt, HMP. See, folks, whenever G6PD is going to allow this reaction to happen, this to go to this, let me put this G6PD underneath because I have to use the top. G6PDH is going to be able to do another coupling reaction. What is coupling reaction? There is a molecule here. This poor molecule here is called NADP+. It is oxidized. It has lost its electron. This is not going to be able to do what's supposed to do. There's a function for NADP. But when it's oxidized in this form, it's not going to be able to do it. But when you are using the G6PDH to go ahead and get glucose 6-phosphate into a pentose sugar or pentose phosphate. What's going to happen here is that you're going to couple that with the reaction that's going to give a hydrogen to NADPH, NADP, and it's going to make NADPH. Now, this is a reduced molecule. This is the molecule that's supposed to be able to do what's supposed to be able to do. It's going to be able to actually do it. Okay? Now, what is that thing that NADPH is going to be able to do that's so important? It's very simple. See, folks, you are going to have oxidative environment inside of the cells. Every cell is going to have oxidative environment. That's one of the things, like we are living in our homes, we generate garbage. Okay? Think about garbage as being the oxidants. Red blood cell has metabolism. It's going to generate garbage. Those are going to be oxidants. One of those oxidants is the one that ladies, you use that. Sometimes guys do the same thing. I don't know, not ladies, but people use that to bleach their hair. Hydrogen peroxide. You want to bleach your hair, this is what you're going to go ahead and use. Okay? You generate that inside of the red blood cell. This is a strong oxidant. You know what happens if this comes across the DNA? It's going to oxidize the DNA. The DNA is not going to be able to do what it's supposed to do. If it's going to come across the proteins, it's going to oxidize the proteins. They're not going to be able to do what they're supposed to do. So you got to get rid of this. How are you going to be able to get rid of this? There is an enzyme called glutathione reductase. I want to show this as a symbol GSH. This is reduced. This is ready to get the business done. This is ready to work. GSH. But let me tell you how I'm going to go and depict the oxidized version of the same enzymes. We're going to call this GSSA. GSSG? How do they use book? I think your book uses H. I think this is I don't remember, but the point is going to stay the same. This is going to be the oxidized version. What am I telling you in here? What I'm telling you is a very simple concept. That if I want to get rid of this guy that is generated inside of the red blood cell, I have to have this enzyme in its reduced form. How am I going to be able to do it? You see that hydrogen up here? This hydrogen is going to be combining with this H2O2, and the product is going to be 2 water. You're going to go through a product and you're going to produce water. Water, 70% of your body is going to be water. Water is not going to be toxic. H2O2 is. The point is that I'm getting rid of it. Now the thing is that every time that you're going to go ahead and use this NADPH, okay, anytime that you're using, so you are having, let's put it like this to not mix up the hydrogen. This is oxidized form. NADPH enables the oxidized glutathione to become reduced. And the reduced glutathione is going to be oxidized whenever it's going to react with hydrogen peroxide, in turn producing water. About 10% of the glucose energy is going to go toward making this pathway. Okay? In order to make sure that you are not going to have too many oxidants in the environment. Because if you are having that oxidant, your membrane lipids are going to become oxidized. If your membrane lipids are going to become oxidized, have you guys looked at these red blood cell morphology that I'm showing you in the laboratory? Haven't you wondered why these red blood cells look the way that they look now? Well, these are the things that happens. When the red blood cell's membrane is going to become oxidized, it's going to start having different morphologies. It's going to have a different morphologies that they're not going to be able to do what this cell is able to do. Okay? So what's going to happen here is that NADPH in here, where did it come from? From the hexamonophosphate pathway, or shunt. Okay? It came from this glucose 6-phosphate. Instead of going directly toward the pyruvate, it went to a shunt. It reduced NADP to NADPH. NADPH was able to go and reduce the glutathione that was oxidized into the reduced form, and the reduced glutathione is able to combine, react with the hydrogen peroxide and generate water, problem solved. Okay? There is another pathway in here that's going to be, my God, this place is hot. Whew. This is going to be methemoglobin reductase pathway. It's going to come a little bit lower down here, in this area. Methemoglobin reductase pathway. So what this is about, again, you don't generate any ATP in this case. Why we are doing it? The fact is this, people. Hemoglobin, red blood cells are responsible to carry oxygen. Oxygen is the strongest oxidant. It oxidizes things. Haven't you seen the, rust? What is rust? When oxygen binds to the iron, it's going to cause the rusting. It's going to oxidize the iron. You already know, I'm going to discuss it in great detail today. You already know hemoglobin has iron in it, right? Everybody knows, just you know that much. That iron can become oxidized. Yes, I know that the shape of the hemoglobin is somehow that is going to prevent the exposure very much, but still the system is not perfect and is going to cause some of the hemoglobin to, some of the iron in the hemoglobin to become oxidized. That's going to be called methemoglobin. So when you are having a good hemoglobin with a good iron, that iron is going to be in reduced state. I just told you. It's going to be in reduced state. This is the reduced state of iron, Fe2+. Whenever iron becomes oxidized, it's going to move into the F3+. This is called ferrous. This is called ferric. Which one do you want in a good hemoglobin that is able to do what the hemoglobin is supposed to do? Ferrous. Ferric is not a bad guy. I don't want you to develop animosity toward this ferric iron. You need it sometimes. This is the way. This is the way it makes complete sense if you think about it. This is the way that your body is able to transport iron in your body. Think about it. If you are going to go ahead and take iron from one point in your body to another point in your body, from your intestines to your bone marrow, you don't want the iron to be in this state. Why not? Because it's going to bind to everything and it's going to become oxidized. You're going to turn it oxidize yourself, you carry it where it's supposed to go and reduce it at the site, and then that iron is going to be able to do what it's supposed to do. Okay? Makes complete sense. So methemoglobin reductase is necessary, and this pathway is going to use another molecule that is similar to that NADPH, but it's not that one. It's NAD+. It's going to become NADH, and that NADH is going to allow this methemoglobin reductase to become reduced, which is going to be able to convert methemoglobin into normal hemoglobin. Questions so far? Okay. By the way, I was looking at your textbook and I noticed that there's a chart on chapter 9. Good chart, but there are a couple mistakes in it, so be very careful. What I just told you is accurate in here, and that's going to proceed over whatever is in the book, because the book has mistakes in it. That chart has a couple mistakes in it, okay? There is one more shunt pathway. Don't lose the perspective here. Don't lose the perspective. The purpose was that every place else, every other cell that's going to do glycolysis, you're going to have the glucose go through this pathway. Either it's going to go this way or it's going to go that way. You're going to be able to generate ATP. But we talked about the red blood cell doesn't have mitochondria. It's not going to go that way. You are going to generate the ATP while going through here, but there are 3 shunts, 3 extra pathways that's going to go through. The last one is going to be the most interesting in my opinion. Well, they're all interesting, but it's going to be interesting in a sense that this pathway not only does not produce any ATP, but this pathway is going to use 2 ATPs. It's going to use 2 ATPs. So by the time that you get out down here, there is no more ATP produced. So you go through, break down the glucose all the way down here. If you go through this next pathway, you're not going to generate any ATP. That doesn't make sense. As if you go out and work for somebody and you don't get your paycheck at the end of the month. How many of you are willing to do that? Doesn't make sense, right? Unless you're a volunteer, but that's a different story. All right, what is the name of that pathway? It's called Rappaport Lubering. So I'm going to erase this to put it on this side. Rappaport Lubering pathway. Now again, I am not emphasizing on the intermediates, the name of these molecules too much, because this is not the chemistry class. If this was a biochemistry class, you would have to know all of these things. That's not the purpose. I want you to understand what is the purpose here. The purpose is in here is going to be the third pathway called Rappaport Lubering is this. One of the intermediates in here. Okay? One of the is going to be 3 this phosphoglucarate. This molecule is going to be one of the intermediates right up here. Or it's going to be 1,3. Okay? That name is not important right now. This is going to be diverted into this pathway. What's going to be the outcome of that pathway? You're going to use up 2 ATP in order to convert this molecule into 2,3 bis phosphoglycerate. What is that? That's a long name. I know it's not, so let's go ahead and make it shorter. We're going to call this from now on 2,3-BPG. That's the name that you should know. So you are telling me, or perhaps I am telling you, I am telling you that this glycolysis pathway is going to be shunted into this Rappaport Lubering pathway. Not only you're not going to generate any ATP, but you are also going to use 2 ATP. I want to make this story even worse. When you come from here to here, then this is going to go back to this pathway. There is an area in here you make 2 ATP. You're going to skip that. So not only you don't make any ATP, you use 2 ATP, and you skip this stage or step that you're going to make 2 ATP. This is going to get really worse. So it's going to be just as if you go in and work for somebody, and at the end of the month, you write a check for them instead of they write a check for you. How many of you are going to like that? There's a reason though. There is a reason though. This is going to influence the release of oxygen at the level of tissue. Let me tell you this, even though this is going to be lecture 10 that we're going to cover in here too today, but let me go ahead and tell you right now. Hemoglobin is going to have, each hemoglobin molecule is going to have 4 heme attached to it, heme molecule attached to it. Each heme is going to have iron in it, and each iron is going to be able to bind to 1 oxygen. If this guy is going to be around, hemoglobin wants to let go of oxygen. If this guy is not around, hemoglobin is going to be very happy bounding to the oxygen. Now let's put it in perspective. Let's put it in perspective. You told me in the beginning of this class the function of the hemoglobin is to carry oxygen from the lungs to the cell. Everybody agree here? Okay? Now, you got to ask yourself, how is that possible that hemoglobin knows that it's supposed to bind to oxygen in your lungs, but when it gets to the level of the tissue, it has to let go of the oxygen? How does that process work? And that's going to be a very deep discussion we're going to have today. But right now, I want you to understand this. If this guy is going to increase at the level of the tissue, it's going to force the hemoglobin to let go of the oxygen. So oxygen is going to be released with ease, not problems. Okay? We're going to come back to this 2-3 ppg. All right, I told you what I wanted to tell you about this. So let's just go ahead and get to the lecture. So I already told you everything I wanted to tell you in here. Explain to you all these details, different shunts and pathways in glycolysis. We're going to talk a lot about the red blood cell membrane today. Because all these various shapes that you see in the laboratory, there is a reason for every one of them. And you're going to learn, starting today, why we are having target cells. You're going to learn why we are having acanthocytes. You're going to learn why we are having spherocytes. You're going to learn why we are having erythrocytes. Because there is a reason for all of these things. Okay? So that's what's going to be the primary discussion here. I explained that to you about glycolysis, the different pathways it can go. I told you about G6PD deficient, glucose 6-phosphate dehydrogenase. But what I have not told you is that G6PD deficiency is the largest number of, when it comes to people who are inflicted with this, is going to be the largest enzyme deficiency in the world. There are 400 million people in this world that they do have deficiency of G6PD. They got a mutation in the gene. G6PD is not going to be able to do what it's supposed to do. What was the function of G6PD? What did it accomplish? It was able to reduce the, ultimately, making NADPH, which is going to reduce the glutathione in its reduced form, which was able to go ahead and neutralize the oxidants such as hydrogen peroxide, right? Now, if 400 million people in the world, they don't have this enzyme working right, what is going to be the outcome? What do you expect from these people? They're going to have a lot of problems, especially it depends on the environment that's going to be oxidative environment. Let me give you one example. Do you know what fava beans are? Fava beans. Fava beans. If you have ever eaten, in a Thai restaurant or a Chinese restaurant, or fava beans is a type of bean. That bean, or Mediterranean. If you have ever had hummus, you have eaten and tried fava bean. You might not know what the bean is, but is it spelled like this? Fava bean. Okay, bean, like Mr. Bean. For whatever the reason is, when people consume fava bean, it's going to increase the oxidative environment in their body. Let's say I'm a person with G6PD deficiency. My mom made me hummus and I sat down and ate the whole container. 6 hours, 10 hours, 24 hours later, I start feeling bad. I turn yellow and I start getting sick. They take me to the hospital and they look at my blood, they see my hemoglobin is going to be 8. My hematocrit is 30. Are those normal numbers? What happened? I was just enjoying my fava bean and all of a sudden, I'm dying. Because of the fact that fava beans introduce oxidative environment to your body. When you're having oxidative environment, a normal person has a glutathione that is going to be able to function properly in order to get rid of those oxidative environment factors, right? But this person can't. So what's going to happen here is that hemoglobin is going to become oxidized. When hemoglobin is going to become oxidized, what's going to happen here is that hemoglobin is going to become denatured. Not only that, your membrane is going to become oxidized. Your membrane, when it becomes oxidized, is not going to be able to change its shape anymore. these red blood cells that are going to be succumb to that situation, when they go through the spleen, they're going to get cut, and macrophages are going to break them down. What's going to happen? What's going to happen is that red blood cell hemolysis. All those red blood cells are going to start to hemolyze, okay, to hemolyze. Now, in that situation, there are several things that may happen. If you be able to stabilize the patient, you're going to be fine. The patient is going to come back, and after a week or two, is going to be able to get back on his or her feet, and everything's going to be fine. But if the patient doesn't get stabilized, and if the hemolysis is going to be rupturing the red blood cells, is going to be too great, you're going to start losing a lot of these things through kidney. First of all, free hemoglobin is going to be toxic to your kidney, okay? And free hemoglobin is going to be filtered through glomerulus. It's going to be filtered. If there is too much of it, you're going to absorb some of it back into your body, but if there is too much of it in a hemolytic crisis like this case, it's going to go through your urine, okay? So you're going to lose the iron, you're going to lose the, these different polypeptides that are making the hemoglobin. Whenever you are going to go in a situation like that, if you are going to have the extravascular hemolysis, remember there were two types of hemolysis last time we talked about briefly at the end of the class. You got extravascular and you got intravascular. Where is extravascular is going to happen? In the spleen, in the liver, but primarily it's the spleen. That's the time that macrophages are going to sequester the red blood cells, recycle them without causing any problem. But if you are having a membrane of the red blood cell that is not as flexible as it should be, so what's going to happen is that some of these red blood cells are going to rupture in the circulation. And when they rupture in the circulation, their hemoglobin is going to be released, right? That hemoglobin, you got a protein. You should know this name. You got this protein called haptoglobin. Right now, you have it in your blood traveling. Haptoglobin. Haptoglobin, your liver produces this protein. Haptoglobin has one function: to grab free heme and take it to the liver in order to process that. So you don't want, when the hemoglobin is going to be bound to the haptoglobin, it will not go through the kidney anymore. You would be able to take this to the liver, and you would be able to extract the iron, you would be able to recycle the polypeptides, and you would use everything. Now, if tomorrow somebody comes and asks you, somebody on your board exam is giving you a question, and he's asking you what is the problem with this patient, and they have a bunch of different results, and you can see one of those results is haptoglobin, and you can see that haptoglobin is way below normal. What is the first thing that's going to come to your mind? Be specific. Extravascular hemolysis or intravascular hemolysis? If you learn what I just told you, you're going to be grateful 2 years down the road. One day something is going to happen to you, and you're going to say, oh, damn, Dr. Nasser, he told me that on that day. Remember that. Your haptoglobin goes below normal. That's going to be indicative of intravascular hemolysis, not extravascular hemolysis. Okay? All right. So G6PD, we understood the purpose, and we understood why it causes hemolysis, because oxidation of the proteins in the red blood cells are going to reduce the age of that red blood cell. It's not going to be able to go the full 120 days, and is going to be removed from the system quickly, causing hemolysis. Now, the bite cells, degmocytes. You have seen some of these. Some of you call it helmet cells. Some of you call it bite cells. But the medical name is degmocytes. Either one, fine with me. But why? Why we are having a red blood cell that a macrophage took a bite out of it? Why? The answer is very simple. This is going to be quite common among people with G6PD deficiency. It's not going to be the only reason. You will see bite cells in many different conditions, okay? But one of the most common ones that you're going to be able to see when you are looking at the right stain is going to be in case of G6PD deficiency. Because of the fact that hemoglobin, I told you, is going to be oxidized, and you're not going to be able to see any of these things in a right stain. But if you get that blood from a G6PD deficient person and do a methylene blue, you will be able to see inclusions inside of this red blood cell. But you're not going to see it with the right stain. You have to do it with this special stain. In this case, this stain is going to be new methylene blue. What you are having, these inclusions are called Heinz bodies. Heinz bodies are nothing but denatured protein. In this case, this denatured protein is going to be hemoglobin that were oxidized. Red blood cell is going to be, macrophages in the spleen are going to be able to remove these Heinz bodies from the red blood cells. And when they remove it, because the rest of the red blood cell is in pretty good shape, the membrane is going to close down, just a piece of it is going to come out, and this is what you're going to be able to see in its place. A cell that has a piece of it removed. It's going to indicate Heinz bodies. So anytime that you are looking at the red blood cells that has a lot of phagocytes, if you do new methylene blue, it is very likely that you will have Heinz bodies. What is Heinz bodies? Denatured hemoglobin. Okay? That's one. You understand where that's coming from now. Any questions? Membrane. So I already told you a lot about the membrane of cells, but in this case, red blood cell membrane is going to be a very unique membrane, but it's going to be very similar membrane to other membranes. What is going to be similar? There is going to be a large composition of lipids. There is going to be a large composition of proteins. There is going to be a composition of carbohydrates. Each one of them is going to have a different task. The lipids, bilayer phospholipids, the phospholipids are going to be creating this boundary between outside and inside of the cell. But I want to emphasize now, perhaps I didn't emphasize this last, when we were talking about the membranes, that when we are talking about membranes, phospholipids are a very important component. But they are not all the lipids that you find there. You have a lot of cholesterol molecules there. Cholesterol molecule is going to have a very important function when it comes to red blood cells. For any cells, but especially for the red blood cells. The ratio of phospholipids to the cholesterol, when we are talking about if you get all the phospholipids, see how many you got, and you look at the cholesterol in the membrane, how many you got? There is going to be a 1:1 ratio. 50% is going to be phospholipid, 50% is going to be cholesterol. When I'm talking about only the lipid component, people, I'm not talking about the entire membrane. If I remove all the phospholipids and I put all the cholesterol in one container, you're going to have half and half. 1:1 ratio. That's a good ratio. That's the way that the normal people are supposed to have the red blood cell in that ratio. As the red blood cell ages, that ratio changes. And that change in the ratio is going to affect the function of the red blood cell, the membrane of the red blood cells. Let me tell you what those are. If you increase the cholesterol content of the membrane, you will increase the strength of the membrane. It becomes a very strong membrane. But you're going to reduce the elasticity of this membrane. It's not going to be able to change its shape anymore. If you increase the cholesterol, you're going to make it strong. You're actually going to make it stronger than steel. If you can imagine how that is, that red blood cell membrane can become stronger than steel. It can. However, if you reduce the cholesterol content, I am talking about 50-50 ratio of the phospholipids and the cholesterol. If you reduce, so you are having more phospholipids and less cholesterol, you're going to increase the elasticity. This red blood cell will become very elastic. Okay? So the integrity of this membrane is going to be very important. That is why oxidative environment is going to affect the cell function so badly. Because of the fact that if these lipids become oxidized, if this cholesterol becomes oxidized, let me give you an example. I just remember something, I can add something important here. This cholesterol is continuously being changed between the plasma cholesterol and the membrane cholesterol. There are enzymes, there are a bunch of different enzymes. Their job is this: get the cholesterol from the plasma and get rid of the damaged cholesterol that is in the membrane, get a good one, put it in place. There are conditions in which you have a mutation in those enzymes. So those enzymes that are able to replace the membrane cholesterol with the plasma cholesterol, you get a genetic mutation. Sometimes they are there, but they're not going to be as effective working. You know what's going to cause? When you are going to have that problem, you're not going to be able to replace the cholesterols effectively. So the cholesterol membrane is going to start developing these unique characteristics depending on what part of the cell you are. The outcome is going to be what we call acanthocytosis. Acanthocytes. You remember those cells? Acanthocytes are going to be, I don't know where to put it to everybody sees it. You would have a red blood cell, there are going to be a spacule, something like that. That's acanthocyte. That's going to be the time that your cholesterol is not going to be replaced effectively with the plasma. So as the cholesterol is going to become oxidized, there is nobody to change it. That's going to cause the membrane to lose its ability to come back together, and that's going to cause the acanthocyte support. Okay? All right. Let me tell you about glycocalyx. Because to me, folks, the only reason that I enjoy science really at its core, I just enjoy science because I understand the science at its basic level. And the questions like this always the reason that I was able to go back and read and understand how science works. I really had this question. I always, my teacher used to tell me that whenever he was going to go and explain about the membrane and things like that, he would give me the example of oil. He would say that, remember, you put a drop of oil in a pot of water, and you put the drop of oil in a pot of water, and they come together. He was just talking about how the lipids are going to stay together versus against the water going to be hydrophobic. The first thing that comes to my mind is that I just don't understand. And I really didn't understand at the time. Why is that all the red blood cells, or all the cells for that matter, but the red blood cells are fluid, so it's easy to give a good example out of them. Why is that all red blood cells are able to travel together? They all have the same membrane. Why when two red blood cells hit each other, they don't fuse? Why they don't become one? The same way that two oil in a pot of water come hit each other, they're going to become a big oil, right? Why that doesn't happen in the red blood cell? That was a question that it didn't make sense. I had to understand it until I came across this, glycocalyx. Glycocalyx are going to consist of the carbohydrates that are going to be on the outer surface of these carbohydrates in here, on the outer surface of red blood cells, or all blood cells, but specifically in this discussion is in red blood cells. They're going to have a net negative charge. So you're going to have this negative charge on the outer part of this red blood cell. And the next red blood cell that is beside of it is going to have the same negative charge. What does negative and negative do? They repel each other. So they're not going to fuse together. They're going to push each other back. Okay, very simple answer and makes complete sense, right? So that's glycocalyx. Bilipids. So I already told you about the composition of this lipid in I think it was second lecture. So I'm not going to go back and repeat everything, but phospholipids, proteins, all those are going to be, these are cholesterol molecules. You see, these are the cholesterol molecules. I know when you count the number of phospholipids, you have more than any other molecule. But if you're going to measure the mass of what is in here, you actually have more proteins, because some of these proteins are really more massive than many phospholipids. So you actually have more protein composition when you're talking about the mass of the membrane. 52% of the membrane is going to be, on average, is going to be proteins. about 48% is going to be lipids, okay? So it's not going to be, but we are talking about the mass. If you are talking about the number of molecules, you have much more lipids than anything else. And I think that I already emphasized the fact that these proteins are going to have functions. I mentioned that today one of the important functions are going to be the pumps that are going to be responsible to maintain the gradients of ions. You got to have 12 times sodium concentration outside than inside. You got to have 25%, 25-fold higher potassium concentration inside than outside. How are you going to make that happen? With pumps like this, which are going to pump the ions, against their gradient by using ATP. These are going to be part of the membrane as well. Red blood cell deformability. Now I know some of these pictures you don't have it. I was going over the lecture and I found this and I thought when I come across something that I think that helps you guys, I immediately put it in lecture. So just be aware of it. Don't be surprised. You didn't do anything wrong. I just added this because I found it really makes the point. Look at this. This is going to be, I think this is something about 2 microns in diameter. This canal in here. You are having a red blood cell that is able, look at the time, less than a second is able to change its shape. If you had a wrong ratio of cholesterol to phospholipids, it would not be able to change that shape that quickly. It's able to go through in small canal and is able to come out, and when it comes out, back to normal. That's a healthy red blood cell membrane that is able to go in and do that. As the red blood cell becomes older, this ability is compromised. Now you understand why the spleen is the site that these red blood cells that are getting older are going to be sequestered and they're going to be recycled. Okay? The concept of deformability is the ability of the red blood cell to change its shape. You know, guys, what's going to happen here is this. When you look at the surface area of a normal red blood cell compared to the volume of the normal red blood cell, 90 femtoliter, I think about 140 cubic micrometer, what's going to be? There is a 40%, there's a 40% extra surface area compared to the volume. So you got 40% extra membrane compared to the volume. That's why you're able to have the discoid shape. If you are losing that membrane, if you are losing that extra membrane, that 40%, this discoid will become this. As this red blood cell gets older, the membrane is going to be lost without you losing the cytoplasmic content, and the cell is going to become spherocytes and it's going to become rounder and rounder until it cannot go through the spleen and it's going to get captured. Okay? Any questions? All right. Another thing. See, everything's coming together. I hope that you guys are not looking at each one of these separately. I hope that you are able to put everything together. Okay? I am talking about the membrane becomes oxidized, it loses its ability to change its shape, it's going to get caught in the spleen. I also told you about the fact that those pumps that maintain that ionic gradient, those pumps that make sure that the potassium is 25% higher, 25-fold higher inside of the cell than the outside, and the sodium is higher outside than the inside. Those pumps are all going to be dependent on ATP. As the cell is going to get older, the ability to produce ATP is compromised. What's going to happen? You lose the gradient. So the sodium that comes in cannot go out. Sodium that comes in is going to bring what with it? Water. The cell from its normal shape is going to become spherical, and what's going to happen to this spherical? Can this spherical red blood cell do this? No. It's not going to be able to do that. And that's the way that spleen is able to go ahead and identify what is older, what needs to be removed, and what needs to go through. Okay? Any questions so far?
Does
Line
it
up.
matter what kind of cholesterol content it is? Like there's LDL and HDL
Oh.
or
What you are saying when you are saying HDL and LDL, those are not cholesterol. That's the misnomer that people use to explain lab results to layperson. Those are cholesterol carriers. Cholesterol is cholesterol. HDL is high density lipoprotein that's going to go in and take the cholesterol from the tissue, take it to the liver. Because cholesterol is a lipid, right? It cannot by itself travel in the plasma because cholesterol is lipid and plasma is water. They don't like to mix, right? So you need the carrier there. And you will have this carrier molecule from the tissue to the liver is going to be high density lipoprotein. From the liver to the tissue is going to be low density lipoprotein LDL. They are not cholesterol, they're cholesterol carriers. Okay, cholesterol is cholesterol. These are going to be carriers. I know that they commonly use bad cholesterol and good cholesterol. Those are for the layperson language. Those are not for CLS experienced professionals. Those are just carriers. Okay, you got to learn that in your chemistry. They will tell you that. Take 5 minutes, people. We got to finish the next lecture. So 5 minutes. And if you finish that lecture, because of Merle, we got to go and finish the next lecture as well. Nah, just one lecture. We got to finish in 5 minutes. I am going to start at 2:06. Just because of you. So don't blame me. Blame Merle. All right. This new lecture, people, is going to talk about hemoglobin metabolism. I'm going to quickly tell you what's going to happen to red blood cells right now, then I'm going to go ahead and place my emphasis on what is going to actually happen to the hemoglobin. How is it going to come into being, and how is it going to be broken down. So remember, we have already talked about this one. Every second you make 1 million red blood cells, therefore every second you have to get rid of 1 million red blood cells. Where does that happen? About 90% of it is going to happen in the spleen. Okay? So what's going to happen here is that you got macrophages inside of this meshwork that is made by the reticular fibers in the spleen. In the red pulp, these macrophages are able to identify cells that are older, and they are able to go in and remove them, and they're going to phagocyte them, and they are able to go in and break them down. Now, red blood cell has what? There are 3 main components that are going to make up the red blood cells. One is going to be proteins. Proteins. Hemoglobin is a protein, right? What does protein consist of? What makes proteins? Amino acids. So there are enzymes inside of that macrophage that are going to break down that protein into its amino acids. Now the amino acid is going to be as if I break down this wall and separate the bricks, and I would be able to use the bricks to make more walls. Okay? So that's going to happen to the proteins. What's going to happen to, there's something else that's very important inside of the hemoglobin. That's going to be the iron. Next lecture, we're going to cover that after the exam, is going to be iron metabolism. How is iron absorbed in the body? At that point, you're going to realize that is a very strict mechanism that's going to allow the iron to be absorbed. You're not going to absorb too much, you're not going to absorb too little if everything is working right. But the bottom line is that you have to preserve iron. You cannot get rid of the iron in your feces, you cannot get rid of the iron in the urine. You're going to preserve it. How? When the macrophages recycle that red blood cell, they're going to get the iron, they're going to go ahead and deliver it to bone marrow. So it can be used in making more red blood cells. Okay? One part is going to be left that we have no way to recycle it. And that's going to be the part we call the heme without the iron. We call that protoporphyrin. That's the name of the molecule. Now this specific protoporphyrin is going to be protoporphyrin 9. What is this? This is heme without the iron. Okay? Where is it made? Protoporphyrin is going to start being synthesized in the red blood cells at the time they are pronormoblast. Think about what we have talked about those stages. Pronormoblast, that's the time you're going to start producing heme. Where is it produced? In the mitochondria. Remember, those red blood cell precursors, they do have nucleus. They do have organelles. In the mitochondria, inside of the matrix of the mitochondria, you're going to be making the protoporphyrin. When the iron is absorbed, iron is going to come inside of the mitochondria, is going to attach to the protoporphyrin, you got your heme. The heme is going to get out of the mitochondria, it's going to go to the cytoplasm. You're going to have the polypeptide chains, the globin chains we're going to call them. These chains are going to come together with this heme, you got your hemoglobin. Okay, that's the way it's going to happen. So macrophages got to get rid of this protoporphyrin, the heme without the iron. They're going to process it because protoporphyrin is not going to be a very pleasant molecule to have in your system. You have to process it. Macrophages are able to process this into what we call bilirubin. At that point, when the macrophages process this to the bilirubin, this bilirubin is going to be unconjugated. For the purpose of this class, what that means, unconjugated, it means it's not dissolvable in water, it's not soluble in water. What's going to happen to it? Well, bilirubin is going to be given in its unconjugated form, and it's going to be given to a carrier molecule such as albumin. Albumin is going to be soluble in water. If this is the bilirubin, look at my hand. If this is the bilirubin, this is the albumin. This is not going to dissolve in the water, in the plasma, but this will. Okay? So albumin is going to pick up this unconjugated bilirubin and is going to carry it to the liver. Liver is going to go ahead and conjugate this bilirubin. There is this molecule called glucuronic acid. Which in liver, you're going to get 2 glucuronic acid, you're going to bind it to bilirubin, you're going to conjugate the bilirubin. When you conjugate the bilirubin, then you're going to mix it with cholesterol, you're going to mix it with salt, we call them bile salt, and you're going to put it, make something we call bile. You're going to put it in your bile ducts. Anatomy and physiology. Where does the bile ducts go to? Where? Louder? What part of the small intestine? Duodenum. That's right. They're going to empty the duodenum. Don't come and tell me you didn't learn something new today. I just told you why the color of your feces is brown. And this is something, I'm not joking, I'm serious. It's because of the bilirubin. Without the no, it's funny. Sounds funny. But next time you're working in a hospital and you see a patient is having a feces that's going to be white, what comes to your mind first? There is a problem with that pathway. Perhaps there's a gallstone is obstructing the pathway of bile being emptied into the duodenum. That's why there is no color. Think about these things in this manner. Makes sense out of it. Okay? It's okay to have a good laugh. I'm all for the laughs, but as long as you get something out of it. Okay? So that's what's going to happen. That's the journey of the recycling of the red blood cells. You're going to break it down in the spleen. You're going to get rid of, recycle everything that you can. Whatever you're not going to be able to get rid of, protoporphyrin, you're going to process in the bilirubin. Bilirubin is going to be unconjugated, bound to the albumin, travel to the liver. Hepatocytes are going to conjugate it by binding to 2-glucuronic acid. It's going to become water soluble, put it together with a bunch of other things, put it in the bile ducts, and it's going to go into the small intestine, duodenum, and in there is going to have a very important function. It's going to have a very important function in lipid absorption, but that's, I'm not going to talk about it right now. Now let's talk a little bit about the heme, about hemoglobin itself. Let's look at the hemoglobin just a bit. Everything that I told you is up here, people. If you are wondering that, well, I keep brought this right, everything is up there. Okay? Heme is a macromolecule. it has different polypeptides coming together in order to make a competent molecule. Okay? In the case of this hemoglobin, you are going to have 4 polypeptides. These 4 polypeptides are going to make a pair of homodimers. What does a homodimer mean? Homodimer means in this you got 4 polypeptides in here. 1, 2, 3, and 4. 2 of them are the same. Beta 1 and beta 2 are the same. Alpha 1 and alpha 2 are the same. That's what homodimer means. Means dimer means there are 2, homo means they are the same. So they are going to be 2 and 2 are going to come together and they're going to match up in order to be able to generate a competent hemoglobin molecule. At the center of each one of these polypeptides, you are going to have the heme molecule. I told you already the story. The ontogeny is going to be that is going to be produced inside of the mitochondria. It's going to come to the cytoplasm and it's going to bind to the proteins now to make the heme. So the production of the hemoglobin is going to happen in the cytoplasm. The production of the heme is going to happen in the matrix of the mitochondria. Okay? These are going to have genes. There are proteins like any other proteins, they're going to have a gene. Okay? There are 2 genes. No, I'm going to retrace my statement. There are 2 family of genes that are going to be responsible to make all the proteins. We call them globulin chains for the hemoglobin. One family is going to be sitting on chromosome number 11. There are 2 genes on that. One is for alpha, the other one is for zeta. Zeta. Alpha. What chromosome was that?
11.
You got another family that is going to be on chromosome number 16. That's going to be covering beta, gamma, delta, and finally epsilon. So on chromosome number 16, you're going to have these 4 genes. They're very close to each other. They're evolutionary, they're connected to each other. They're going to be very close to each other. Every hemoglobin molecule, so the hemoglobin composition, which are the polypeptides, is going to change depending on the stage of development. So if you are an embryo, it's going to be different. If you are a fetus, it's going to be different. If you are newborn, it's going to be different. If you're an adult, it's going to be different. It all depending on the need of the body. Let me put it in perspective. A fetus. Where does a fetus, you know that the fetus doesn't use their lungs. They're not breathing in the amniotic fluid. Where is the fetus getting the oxygen? From the mother through the placenta, from the mother. Now, again, one of those stupid questions that always comes to my mind. Why does oxygen why is it going to go and let go of the hemoglobin of the mother, cross the placenta, and bind to the hemoglobin of the fetus? Why?
Stronger attraction.
Because of the fact that it has a stronger attraction because it's a different hemoglobin. So if you're having a fetal hemoglobin, you want a hemoglobin has a stronger attraction than mother's hemoglobin to oxygen. That's the reason that oxygen lets go of the mother's hemoglobin and comes to the fetus. Because this is an adult hemoglobin. You got 2 alpha and 2 beta. Fetal hemoglobin, you got 2 alpha and 2 gamma. That's going to have much higher attraction to the oxygen. That's why oxygen comes across the placenta from the mother to the child. Okay? All right. So let's continue going through this. This is heme. Imagine this iron is not in here. What's that molecule called? Protoporphyrin. Okay? When you add the iron, you're going to have heme. Look at the reduction status of this iron. Is it ferric or is it ferrous? Ferrous is Fe2+. Make sure you remember that. A competent hemoglobin always has to have iron in a ferrous state, not the ferric state. I told you where that's produced. So when we are talking about the hemoglobin, I already told you this part as well. You know, you got the heme, you got the iron, you got the protoporphyrin, you got the proteins, globins, and when you recycle the red blood cells, everything is going to be recycled except for the protoporphyrin of the heme. Okay? Now, remember, these are going to have genes. All these proteins are going to have genes. Genes are going to be transcribed, then translated into these proteins. But that's not all. You got to realize that probably from your biochemistry courses or anything biology courses, you're going to remember that a protein has several different structures. We refer to them as primary, secondary, tertiary, and quaternary structure. What is the primary structure of the protein? The primary structure of protein exactly is the sequence of amino acids. Now that's important thing, people. Just if you want to understand science, this is simple concepts like this are the key. Let me give you one example. You want to understand why genetic diseases cause disease? Genetic mutations cause disease. You want to understand that? The answer is right in front of you. If a mutation changes the DNA sequence, that instead of having a lysine, imagine this is a lysine, the one that's going to be in here. You have an amino acid that's going to have a big negative charge instead of lysine because you have the mutation. Now this protein, imagine this is going to be a negative charge in here and you have a negative charge in here. These two negative charges are going to repulse each other. The shape is going to change. Do I have to get my key out again? This key can open the door to my house. If I bend it, is it gonna be the same key? Is it gonna be able to open the door? No. If this protein changes its shape, it's not gonna be able to do that. Now, this protein has a function. That function is not gonna be done. You have disease. Bottom line. That's the general for all of these conditions, genetic mutations. Okay? Primary structure, sequence of amino acids, very important, but it's not gonna be everything. Because we already talked about proteins are going to go to endoplasmic reticulum. They're going to go to Golgi apparatus. What's going to happen to them? Well, they're going to get secondary structure. What is a secondary structure? Well, the primary orientation of the proteins, if I'll be able to go ahead and turn on the light here and draw it up here for you to make my point. There are two types. You got alpha helices and you got beta sheet. Now, I am going to draw lines, but these are amino acid sequences. These are polypeptides. So be aware of that. If I am drawing, for example, this is a protein. These lines are amino acid chains. You're going to have no secondary structure, but you might have alpha helix secondary structure. Then you might not have any other structure. Then you're going to have beta sheet structure. Every protein that you're going to be able to see consists of alpha helices, beta sheet, or no structure. But when you put all of them together, you're going to have the secondary structure of that protein. Alpha helices and beta sheets. And that is going to develop because of the interaction between amino acids. Okay? Positive attract positive, negative, positive, opposites are going to attract each other, the same charges are going to repulse each other, and all that. These orientation is going to cause a tertiary structure. The way that the protein is going to fold on itself. That folding is going to be very important. Let me give you one example so you understand what we're talking about. Remember, imagine this is going to be one of those globin chains for the hemoglobin. You have your iron in what state in the hemoglobin? In the ferrous state. You have to dig that iron deep into this polypeptide. Because if it's going to stay on the surface of this polypeptide, every oxidant that's going to come across that molecule is going to go and oxidize it. You've got to hide it in there. That hiding requires a shape of this protein. If that shape is affected, the iron is going to be exposed, it's going to become oxidized, and you're going to have methemoglobin, which is not going to be able to do what hemoglobin is supposed to do. So the tertiary structure is very significant. But sometimes you got large molecules, such as hemoglobin, that you're not going to have only one, you're going to have a bunch of them. In this case, 4 of them. You got an enzyme, RNA polymerase in your nucleus has 150 different parts that come together. Hemoglobin is simple when you compare that to that enzyme like that. But in the case of hemoglobin, you got 4 of these guys fit together like a jigsaw puzzle in order to make a competent hemoglobin molecule. Okay? So these structures are going to be important at every stage, and any compromising these stages is going to affect the function of that ultimate product. So again, different time in your life, you're going to produce different type of hemoglobin. I think there's a chart in here. Let me go to the chart and explain. Okay, here. So again, these are epsilon, zeta, alpha, gamma, beta, and delta. You can see the production of the epsilon and zeta is the first 2 months, 2.5 months after conception. Mostly during embryogenesis in that period of time. Their expression, these are genes. Expression is going to go down. But as their expression is going to go down, you're going to see the expression of other genes is going to come up. You're going to be able to see alpha is going to pick up. And it's going to become predominant. In even fetal life as well as in adult life, alpha is going to be dominant. You also see another one, gamma. This gamma has high affinity to oxygen. This gamma is the reason that you are able to get the oxygen from mother's blood into the baby's blood because of this gamma. But you can see what's going to happen to this gamma after birth. It's going to drop. Average person, adult person is going to have 1% to 2% fetal hemoglobin in his or her body because of the fact that after birth everything is going to drop. But when something drops, you got to replace it with something else. You can see as the gamma is going to drop, beta expression is going to go up. It's going to replace it. And there is another one called delta that is going to stay about 3%, 3 to 4% in an adult hemoglobin. But we will talk about that because depending on the diseases, hemoglobinopathies, the ratio is going to change. Okay? The ratios are going to change. Now, remember, hemoglobin is going to have a pair homodimers. So any hemoglobin that you are going to look at, any type of hemoglobin, is going to consist of 2 pairs of homodimers. Now, what is the orientation is going to be? You always will have alpha-like and non-alpha-like. What does that mean? Alpha-likes are going to be alpha and zeta. Okay? Non-alpha-likes are going to be beta, gamma, delta, and epsilon. You will never make a hemoglobin, well, actually you make a hemoglobin molecule from one of these only, but that's disease. In a normal person, you will never combine the same, you're not going to have a hemoglobin molecule that consists of 4 polypeptides that are all alpha-like. You will never have 2 alpha and 2 zeta together. You will never have 2 beta and 2 gamma together. You don't have that. You always have alpha-like homodimer with non-alpha-like homodimer coming together and make a whole hemoglobin molecule. Okay? In that case, the division of the hemoglobin is going to be divided based on different names. These different names are called GAR1, GAR2, Portland, hemoglobin F, hemoglobin A1, hemoglobin A2, and hemoglobin A. GAR1 is the time that you have a hemoglobin that consists of the globulin chains is going to be 2 zeta and 2 epsilon. GAR2, when you have 2 alpha, 2 epsilon. Portland, when you have 2 zeta, 2 gamma. Hemoglobin F, when you are having 2 alpha, 2 gamma. Hemoglobin A, which is the most predominant in an adult, is going to be 2 alpha, 2 beta. And hemoglobin A2 is going to be 2 alpha and 2 delta. Okay? 2 alpha and 2 delta. In an adult, you will have 97% hemoglobin A. What is hemoglobin A? Because I have seen that people make mistake understanding this. What is hemoglobin A? Can anybody tell me what is composition of hemoglobin A? 2 alpha, 2 beta. What is the composition of hemoglobin A2? 2 gamma. No, 2 delta. 2 delta. 2 alpha, 2 delta. And fetal hemoglobin is going to have 2 alpha and 2 gamma, right? 97, and these are averages I'm giving to you. It might be a little bit more or less depending on the person. 97% of your hemoglobin, 95% of your hemoglobin is going to be hemoglobin A, 2 alpha, 2 beta. About 3% of it is going to be hemoglobin A2, and the remaining 1 or 2% is going to be fetal hemoglobin in an adult. Okay? That ratio is going to be important in the sense that if I have a disease, think about this. If I have a disease in which I cannot make beta hemoglobin, not beta hemoglobin, but beta globin to make the hemoglobin A. Hey, I gotta breathe somehow. Oxygen needs to be carried from the lungs to the tissue somehow, otherwise we'll die, right? So what's gonna happen, you can see the other type of hemoglobin are gonna go up. You will see that the, I told you that the A2, 2 alpha and 2 delta, are going to be about 3%. If I cannot make my beta chains, you're going to see that the same hemoglobin is going to be 40%. Because I cannot make beta chain. Who's going to replace the beta? You're going to see my fetal hemoglobin might be 25%. Because they are replacing, they're trying to compensate for what I cannot make. Okay? Just think about how that's going to work out. All right. So what you are having up here is called, I'm going to give you a full name because I can see being abbreviated over and over, so I think it would become confusing for the students. This chart that you see up here is a very important chart. And I strongly suggest that you understand this chart because you will have many questions out of this chart on your exam next week. This is called hemoglobin oxygen dissociation curve. Hemoglobin oxygen dissociation curve. Okay? Pay attention what you are having in here. On the y-axis in here, up here, y-axis, you are having the percent hemoglobin that is bound to oxygen. Percent hemoglobin that is bound to the oxygen. Down in here, you got the partial, in the x-axis, on the x-axis you got the partial pressure of oxygen. Partial pressure of oxygen. Does anybody know what partial pressure is? Okay, let me go ahead and give my version of partial pressure. Don't go ahead and tell these things to your physics teacher, okay? Your physics teacher is going to have a heart attack with my explanation. Because I'm going to cross the point, even though it might not be exactly accurate, but I will make the point that you need to understand before you go further in here. What is pressure? You should know that one. If I tell you there is this box in here, this box has 760 millimeter of mercury pressure in it. What does it mean? Explain it to me like a 2-year-old. Physics. I'm a 2-year-old. That is more complex. It's a very simple concept. It means there are molecules of gas in here that are pushing and hitting the wall of this container, generating a force of 760 millimeter mercury. That's all there is to it. Okay? Now, if I have this box and I have 10 oxygen molecule and 10 CO2 molecule, and let's, for the purpose of understanding the concept, let's say that inside this box we have a pressure of 20 millimeter of mercury. 10 from CO2 and 10 from oxygen. Okay? Partial pressure of oxygen is going to be 10. Partial pressure of the CO2 is going to be 10. Total pressure is going to be 20. Do you understand what is the partial pressure? It's the pressure that is being generated by that specific gas. So when I'm talking about partial pressure of oxygen, I am talking about the partial pressure of oxygen that is generated by oxygen molecule at the level of the tissue. Okay? In this room, you got 79% nitrogen. You got 20% oxygen. And the rest is going to be other gases that are going to be involved. We know, we have already measured at the level of the sea, the pressure is going to be 760 millimeter of mercury. I just told you 20% is going to be, 21% is going to be oxygen. If you go ahead, multiply 760 by 0.21, 21%, I'm just making the fraction, you're going to get, anybody has calculator in front of them? 100? 59? 160. Let's say 160 millimeter of mercury. This is the partial pressure of oxygen in this room right now. Okay? The pressure, the part of the pressure that is generated by that specific gas of interest is going to be 160 millimeter of mercury. That's what I'm talking about. But in this case, we were talking about this room. In this case, we are talking about the human body, inside of the body. Okay? Now, there is something very important there in here. And that is the fact that this red is what we call a sigmoidal graph, while the blue is hyperbolic graph. Don't get too trapped on the names. Sigmoidal means is S-shape. S-shape. Hyperbolic is, there is no S-shape. It's going to be kind of curved. Okay? That's very important because that's going to talk to you about the nature of the hemoglobin molecule. Hemoglobin molecule has 4 heme. Each heme has an iron. So every hemoglobin molecule is going to be able to carry 4 oxygen molecules. In each red blood cell, you got about 200 to 300 million hemoglobin molecules. So each red blood cell is able to carry 1.2 billion oxygen molecules. Okay? Why is this sigmoidal and the blue is hyperbolic? Because those 4, and this is very important, listen exactly, just listen to what I'm saying, make sure you understand what I'm saying. Because oxygen attachment or binding with the hemoglobin molecule, remember those 4 heme, each one of them has an iron? It is not like that oxygen is able to simultaneously bind to all 4 of them at the same time. It's going to happen step by step, one at a time. The reason is that this is curved is this, that this, when the hemoglobin is not bound to any oxygen. Hey, what is the concentration of hemoglobin that is bound to oxygen here? I'm talking about down here. 0. When the hemoglobin is not bound to oxygen, it doesn't want to bound to oxygen. It's not a favorable reaction right now. It doesn't want to. But if it binds the first oxygen, it's going to be easier to bind to the second oxygen. It's going to be easier to bind to the third oxygen. It's going to be easier to bind to the 4th oxygen. That's why it's sigmoidal. In the case of the fetal hemoglobin, the story is different because fetal hemoglobin has gamma instead of beta chains. So it's going to be hyperbolic. But what can we look and learn from this graph regarding the fetal hemoglobin? Where do you think you're going to be at the tissue level? If I want to put a dot on this chart to indicate to me the level that you're going to have at your tissue, at your cells, at the level of your cells, at the level of your capillaries, where would I put the dot? It's okay, just give me a spot so I can start telling you where you put the dot. Where do I put it in here? Yes or no? I hear combined. Yes or no? Yes? No? Okay. Raise your hand. Yes? raise your hand. Oh, yeah. Thank you very much. Not here, because at the level of tissue, what is the level of oxygen? Is it low or high? This is very high. At the level of the tissue, you got to be in here, right? Now, at the level of the tissue, should I put the dot in here? Still low, but should I put the dot in here? Why not? Because at the level of the tissue, you're not going to have 95% of your oxygen bonding to the hemoglobin. You want the oxygen to get out and go, right? So where would be the best place? Down here, okay? At this point, you are not having any oxygen bound to any, at this point, at the zero. No hemoglobin bound to oxygen. But as you are having the first hemoglobin bound to the first oxygen, everything is going to get slower. So if I have a hemoglobin molecule that is going to push this graph to the left, does that hemoglobin molecule is going to have higher affinity toward oxygen, or is it going to have lower affinity to oxygen? It's going to have higher affinity. And that's why fetal hemoglobin is going to attract the oxygen from mother's blood into the fetus's blood. Okay? That's the reason behind it. Now let's get into this a little bit deeper, because this is an important graph you need to understand. Oxygen delivery, you understand that? Well, let me tell you this, and I'm going to get back to that graph in a second. So you guys understand, red blood cells do a lot of things. The most important one is going to be oxygen delivery from lungs to the tissue, but they're also going to play a very important role in getting the CO2, the waste product, and take it back to the lungs to get rid of. Your red blood cells is going to do a lot of important things, okay? So you got to realize that oxygen delivery is the most important one. There are other things that are going to happen. Carbon dioxide delivery. You got to be able to go and manage the delivery of the waste product, carbon dioxide, either through the kidneys or through the lungs with the help of the red blood cells. I will talk to you about it in a second. Let me get to this graph. If I want to be a hemoglobin molecule in a red blood cell, if I am at the lungs, I have to be up here. I want you to understand why. The reason is why, at the lungs, what is the partial pressure of oxygen? Is it high or low? High. So you got to be on this side, right? You got to be very high. When you are in your lungs, that has a high pressure of oxygen, partial pressure of oxygen, what percentage of your hemoglobin do you think is going to get saturated with oxygen? Or you want it to be saturated with oxygen? High or low? High. When you are in the lungs, almost 100%, close to 100% of your hemoglobin is going to be bound to oxygen. But that's not the same story when you're at the level of the tissue. When you go to the level of the tissue, where do you want to be? Do you want your hemoglobin not to let go of oxygen? You want it to let go. So what you want to do is that you want to be down here. So as the level of the PO2 is going to decrease, you want to also the hemoglobin affinity toward oxygen decrease. So you want to be in here on this side at the level of the tissue. You want to be in here at the level of lungs. And if you are a fetal hemoglobin, or in this example, you are a myoglobin, you want to be on the left side of this graph. Because what is the function of myoglobin? Muscles. You find it in the skeletal muscle, you find it in the cardiac muscle. It's going to do the same thing. So remember this, folks. If I start running a 100-meter sprint, when I stop, yes, I know I'm going to have a heart attack. But before I have a heart attack, what am I going to do? I'm going to gas for what? I just stop. Why do I need to gas for air? If I want to gas for air, I need it when I'm running, not when I'm stopped. Because you used up the oxygen, the first couple of seconds is going to be, you're going to use up all the oxygen that you have available in your muscles. Then this is myoglobin, is actually the original evolutionary speaking, 100 million years ago, you didn't have hemoglobin, you had myoglobin. It divided and it multiplied and they accumulated mutations. But myoglobin does the same thing that hemoglobin does, which means binds to the oxygen. But myoglobin is going to be at the level of the muscle. So when I am running that 100-meter dash, I am going to lose all the oxygen that myoglobin has. So when I'm stopping and I'm gasping for air, because I am resupplying the oxygen to myoglobin. Okay? So do you want the myoglobin to have high affinity to oxygen, low affinity to oxygen? You want it high affinity to oxygen because you don't want the myoglobin to be used up first. You want the hemoglobin to use up all the oxygen that it has, then the myoglobin is going to supply it when the partial pressure is much lower. Okay? So what that's going to do, myoglobin is like fetal hemoglobin, is going to be to the left of this original graph. Now, there are certain factors that are going to influence this graph. Either going to move it to the right or they're going to move it to the left. What are these factors? Number one factor is going to be the hydrogen ion concentration, aka acidity of the blood. If the blood is going to be acidic, which means increased hydrogen ion, you're going to move this graph toward right, which is going to be that hemoglobin wants to unload its oxygen load. It's going to get rid of the oxygen. As you move the graph, when the blood becomes alkaline, as you move the graph this way, the hemoglobin doesn't want to let go of the oxygen. See folks, at the level of the tissue, the PO2 of the oxygen is going to be about 27 millimeter of mercury. That's going to fall someplace around here. Look at the normal range. Look at the normal graph, the red one. At tissue level, about 42% in this case with my finger, it's not very accurate, but around here, 40% of your hemoglobin is going to be bound to the oxygen. Now look what's going to happen as this graph moves toward the left. Same 27%. Same thing for the myoglobin. You're going to have 80% of the myoglobin is still going to be bound to the oxygen. You see, because this one is going to have a higher affinity. There are several things that are going to affect whether or not the graph is going to move left or right. To the right, increased hydrogen ion, number one. Number two, increased temperature. If you are having fever, your hemoglobin is going to easily release the oxygen to the tissue. Temperature, high temperature. And the last one that I want to tell you, what was the name of that molecule that was generated by Rappaport-Luber pathway? 2,3-BPG. If the level of the BPG goes up at the level of the tissue, what that's going to do is going to force the first hemoglobin molecule, when you are having this hemoglobin molecule with 4 hemes that is bound to the oxygen, when the 2,3-BPG comes and sits on the first one, it's going to kick out the first oxygen and is going to replace it. Then what's going to happen is that it's much easier to replace the second oxygen. It's going to come off easier. It's going to be much easier to remove the third one. It's going to come off easier. So as the level of the 2,3-BPG goes up, it's easier to remove the oxygen from the hemoglobin and release it to the tissue. So there are 3 main factors. 1, H+ concentration, acidity. 2, temperature goes up. 3, concentration of 2,3-BPG goes up. They are going to move that graph toward the right. It's easier to get rid of it's easier to release the oxygen from the hemoglobin, or you can say the same thing as less affinity of hemoglobin toward oxygen. Same thing. Opposite conditions. Alkaline blood, low H+, low temperature, hypothermia, as well as low 2,3-BPG, they are going to push the graph toward the left. What does that mean? It means that your hemoglobin won't be bound to oxygen. It means that your hemoglobin will go to the tissue with the oxygen attached to it, but it means that it's not going to be able to let the oxygen go. The oxygen is going to be bound. What's the purpose of that? Is it going to be able to do any good? No, it's not going to be able to do any good. You want the oxygen to be released from the hemoglobin. But if you move, if you are having somebody who has alkalotic blood, if you have somebody who has metabolic alkalosis, what's going to happen here is that that person is going to have problem getting oxygen to his tissue. Because even though the blood is going to be full of oxygen, when you're doing blood gases, you're going to have 98% saturation of oxygen in the blood. But the person is not going to be able to get the oxygen to the tissue because the hemoglobin doesn't let go. Because the graft has shifted this way. Questions? Okay? So it is not linear. See, guys, if these 4 hemoglobin molecules that are attached to each other and that have a heme, if each one of them attached to one oxygen, if they were able to attach to oxygen at the same time, this graph would be linear, would look like a straight line. But that's not the way it happens. Oxygens that are binding to this hemoglobin, to these heme molecules, they do it one at a time. Coming in and going out the same way. When you are going to release the oxygen, it's going to be one at a time. When our hemoglobin is attached to the oxygen, what's going to happen here is that it doesn't want to let go. It's very happy holding to the oxygen. But when the first one goes, it's much easier to remove the second one, it's much easier to remove the third one, and it's much easier to remove the fourth one. That's why the graph is sigmoidal. All right. So shift to the left, shift to the right. I think I covered it up as much as I wanted to. You guys make sure you read it. You email me this weekend if you have any questions, okay? I'll be here on Tuesday. But I am going to, Professor Harris is going to go in and proctor your exam and is going to take care of your laboratory on Thursday. I am in a conference in Minnesota. Temperature is minus 25 degrees. So if I don't come back, I'm frozen someplace. So I am not going to be here on Thursday, so you're not going to see me. Either come and ask your question on Tuesday or email me and I will try to explain everything to you. Okay? I will be here on Tuesday though. Exactly. So what we are talking about in here, same concept. I think I presented that to you. Bohr effect refers to the influence of H plus hydrogen ion on this graph. H plus increases, move the graph toward right. H plus decrease is going to move the graph toward left. So be aware of it. I probably will not give you this graph to the way that it is, ask you a question. I will put it in a case study format. I will put it in a situation that somehow the patient is going to have acidic blood. Then I ask about this graph. You should be able to answer that. That's a fair question. As long as you understand when you are having acidity in the blood, that indicates increased H plus, and that should put you in the right spot to be able to determine what the answer is going to be. You guys got to think in the exam. If you don't think, you're going to have a hard time. Because I'm not going to get things straight from the book or the slides and ask you. I think that would be a disrespect to you guys, folks. I think that would be undermining your intelligence. Chloride shift. I told you that hemoglobin does a lot of things. This is another important thing that it does. So everybody understand where this CO2 is going to come originate. Where is the origin of CO2? Cellular respiration. Waste product CO2. It's going to diffuse from the cell plasma membrane, it's going to come to the blood, it's going to enter the red blood cells. CO2 is going to diffuse into red blood cells. Inside red blood cell, you got this enzyme, carbonic anhydrase. It's going to start this reaction that is going to combine the CO2 with water, is going to give you bicarbonic acid. Carbonic acid is going to be dissociated into H plus and HCO3 minus. The bicarb is going to diffuse out of the cell membrane, out of the red blood cell. So everything in here is happening inside the red blood cell. Bicarb is going to come out, but there is a catch in here. Every time one bicarb comes out, you got to have a chloride ion come in. Chloride ion has to be coupled to bicarb. You got to, if you are losing one negative charge in here, by bringing one chloride charge, you got to keep everything balanced. Okay? Now, some of you are going to get to places that you're going to go and sometimes draw your own blood, and sometimes these are things that are going to happen. Not very often. What will happen? You draw blood and all of a sudden you're going to see that, my gosh, this blood is really red. It's cherry red. What happened? What did you get? You got arterial blood. You got arterial blood. It happens. As the patients are going to be staying in the hospital for longer and longer time and all the veins are going to disappear, what happens is that sometimes you are going to get the wrong, you're going to get into the artery, you're going to get red blood. You're going to get arterial blood. You got to take it to the laboratory. You're going to do a Kim 7. All of a sudden, you're going to get panic value on your chloride. What you going to do? Call the flora and say that it's a panic value? That's a bad thing you're going to do because you didn't pay attention to what I just told you. Venous blood is going to have lower chloride level because of this chloride shift. Arterial blood is going to have a different concentration of chloride ions compared to the venous blood. So be aware of that differences in the concentrations depending on whether or not you're in venous blood or arterial blood. Okay? This is called chloride shift. Bicarb goes out, dissolves, is ion, dissolves in plasma, goes to the lungs, same thing happens, CO2 is generated, you expire and get rid of the CO2. The hydrogen ion cannot come out, it's stuck inside. What it's going to do is that it's going to bind to hemoglobin. It's going to bind to the hemoglobin. Not to the heme, but someplace in the hemoglobin molecule is going to bind to it. Okay? As you are going to bind the hydrogen ion to the hemoglobin molecule, then the hemoglobin, if it has oxygen attached to it, it wants to let it go. So the hydrogen ion goes up inside of the red blood cell. Ability of the hemoglobin to carry oxygen is going to go down. Opposite direction. Does make sense. It does make sense. CO2 came from the tissue. This H plus level goes up in the level of the tissue. Isn't that the place that you want to give the oxygen away? And that's exactly what happens. So there is not just one system that's going to instigate the release of the oxygen from the hemoglobin. There are multiple systems, but they are all doing the same thing, making sure that the oxygen is released at the level of the tissue and is attracted to the hemoglobin at the level of the lungs. Questions? Methemoglobin. You already know what methemoglobin is. Methemoglobin is a condition in which iron of the heme is going to be in the ferric state, F3+. Okay? That is going to go ahead and give a very dark color to the hemoglobin. It's not going to be your normal red. It's going to be more into bluish and purplish color. This person is not painted their face. This blue man is actually has enzyme deficiency. You remember I told you about methemoglobin reductase, also they call it cytochrome P5. That person and his family, I mean, I knew a family, I spent a lot of time in Kentucky, and there's a family, big family that live in Kentucky, and they all have this enzyme deficiency, okay? So they cannot get their methemoglobin and reduce it to the hemoglobin. So this person, for example, is going to have 30%, 40% of his hemoglobin is going to be methemoglobin. You and I have about 1%. He's going to have 40%. That's why the color is going to look like that. Okay? Of course, I can assure you that if this person start taking, 2,000 to 5,000 units of vitamin C, his color changes just exactly like yours and mine. Because vitamin C is antioxidant and is going to be able to do what that methemoglobin reductase does inside the blood. But the bottom line is that this is a condition that is going to reduce the ability of the hemoglobin to carry oxygen. Because oxygen cannot bind to the methemoglobin. Okay? Oxygen cannot bind to the methemoglobin. There is one more thing that is not in here I want to tell you about because it's important. Carboxyhemoglobin. Carboxyhemoglobin. Sometimes you hear that. Carboxyhemoglobin. That might not happen in California very often, but if you live in places that is a little bit colder, You know, not every place looks like this. You're gonna have places that use a lot of heater and things like that, and it is quite common that you hear that, you know, a family of 5 found all dead, you know, in their house. Carbon monoxide poisoning. So what happens is that carbon monoxide, CO, not CO2, CO, is very, very attracted to hemoglobin. Let me put it in perspective what it means. If I have an oxygen molecule in here, okay, and I have, no, let me redo it. If I have a hemoglobin molecule in here, all right, I have an oxygen molecule in here, and I have a CO molecule in the other side of this hallway. That CO, carbon monoxide, will bind to this hemoglobin before oxygen does. Because that carbon monoxide has 240 times higher affinity to hemoglobin than oxygen. And the difference is this: when it binds, hemoglobin binding is reversible. Carbon monoxide is going to bind, it's not going to let go. Carbon monoxide doesn't have smell, it doesn't have color, it's just when the combustion doesn't happen correctly. So what's going to do is that people are going to bed, they are turning the heaters off because it's cold nights, but there is a problem with the heater, so carbon monoxide is going to be produced. They don't smell it, they just get a very deep sleep, and that sleep they're not going to come out of it because all of the hemoglobins are going to be saturated with carbon monoxide. If that hemoglobin is not going to be able to carry oxygen, they suffocate gradually. And it happens so slowly that they are not, most of the time they cannot wake up, okay? And they die. As simple as it's going to get, they will die. So it's something that you always have to take into consideration when you're using this kind of heaters and things like that. They are going to generate carbon monoxide, okay? Any kind of smoking things, any kind of burning things is going to generate carbon monoxide. So those of you who are going to be smokers, I would say that usually everybody has about 1%. You folks are going to have about 3 to 5% carbon monoxide, carboxyhemoglobin in your system. It's quite high among people who smoke, whatever they smoke, as long as they burn it, okay? They're going to have high carboxyhemoglobin in their system. Questions? This is where your exam 1 is going to stand. Up to this point, that's what's going to be covering on your exam 1 next week. That's it, folks.